And thank you very much to the organizers. It's been so far a really fantastic conference, and thank you for inviting me to give a talk. So I'll be talking about the second part of this story, which is about JT gravity coupled to matter. So a different sort of puzzle that has a very similar resolution. So I want to add something to the disclaimer that Pratik said. Also, observers were not hurt so far. I hope you won't get hurt by this talk, so I hope many of you won't be bored since you are observers with a large Hilbert space, but we'll see how that goes. So just since Pratik gave a lot of very nice introductory story, I just want to give some additional remarks. And in recent years, there's been a lot of very interesting progress in quantum gravity, and that was thanks to holography and the gravitational path integral. And most of this progress came from studying black holes. And maybe a very basic way to say why that's the case is that black holes are some macroscopic thermodynamical objects with some temperature and entropy. And we expect that, at least in some regime, we can treat them using semi-classical gravity. But on the other hand, they are fundamentally quantum objects. And if you naively forget about that, sometimes you run into issues. For example, if you forget that you have some finite number of microstates for these black holes, you end up with some puzzles. For example, the black hole information paradox. Now, the gravitational path integral has proven very good at probing some of the quantum features of these black holes, and for example, correctly counting microstates at these steps of Hawking evaporation, and so on. So this seems to be a very good tool to probe these quantum properties of black holes. And maybe one way to say what it does in the page curve calculation is the fact that if you include these replica wormholes in the gravitational path integral, then the path integral at each step of the Hawking evaporation computes the right number of microstates left in the black hole. Now, the kind of puzzles Pratik talked about and I will be talking about originate from the fact that we are treating the spectrum of black holes not as a discrete spectrum, but rather as a continuum spectrum. So the reason why sometimes we incur in these puzzles is because we have now learned that at least in lower dimensions, but to some extent also in higher dimensions, the gravitational path integral seems to compute an average over some ensemble. And this average implies that if you have many theories with a discrete spectrum with slightly different spectra, and then you average over all these theories, you end up with a continuum spectrum. So treating this spectrum as continuum is what causes this puzzle. And so to solve them, we need to probe the discreteness of this spectrum. And in particular, for this puzzle we'll be talking about, will be the discreteness near the ground state. So Pratik explained very nicely that. And there is a sense in which there is a ground state to probe the discreteness of also in this other story that we'll be talking about. And the path integral is able to do that once you take into account for all this higher genus contribution, and you also need to resum the entire genus expansion to probe this effect. So the puzzle I'm interested in is the one that Lin-Maldacena-Rozenberg-Shan raised a couple of years back. And it was originally raised in the BPS sector of JT supergravity. So the fact that it's n equals to JT supergravity. So the fact that it's supergravity is not very important in this story. So the only thing that we will need to know about JT supergravity here is that there is this degenerate ground state, which is given by BPS black holes. And there is this degenerate zero energy ground state has many BPS, many states, which are just counted by some entropy as BPS. Now, the same puzzle arises if you take non-supersymmetric JT gravity coupled to matter, and you restrict to some microcanonical band in JT. So whatever I say here, modulo some subtlety that I will try to point out, and feel free to ask me later, can be formulated, both the puzzle and the resolution, within ordinary JT gravity in a microcanonical band. So what is this issue? So we know that if you look at the thermofield double state of, for example, two CFTs, the dual description of that will be a double-sided black hole. And in general, the thermophile double is a very special state. What you could do is consider some more generic state in which in the preparation of this state in the Euclidean path integral, you insert some operators. And inserting some operators just changes the states and gives you some different black hole spacetime in which you have some particle in the interior and a long wormhole, for example. And this is what sometimes is called the partially entangled thermal state. So the state we're interested in is something that looks like this. It's just a pictorial picture, but what we want to look at in particular is consider this BPS black hole. So these are zero energy states. If you just don't insert any operator in the preparation of a two-sided black hole in this setup, you end up with a maximally mixed state in the BPS sector. In particular, if you look at the entropy of only one side with no insertions, you would get that the entropy of that one side is as BPS, it's just the maximal possible entropy in the BPS sector. Now, what we want to do, and what LMRS did, is inserting operators in the Euclidean preparation. And the operator you want to insert is some primary. And here I'll be talking about very heavy primaries. Projected again onto the ground state. So you insert an operator, project, insert an operator, project. And this projection can be seen as an infinite amount of Euclidean time evolution between any two insertions. So this just implements a projection onto the ground state. So as I said, if you don't insert anything, you have the maximally entangled state. So one side is maximally mixed. This tells you that if you insert operators and change the state, all you can do is lower the entropy. Now, let me try to give you maybe, for those of you that like replica wormholes and islands, an intuition for why you lower the entropy when insert matter. The intuition is that suppose that you're inserting these very heavy particles, and you have many of them, then what you end up with is many different extremal surfaces in between any two of these particles. And those are some degenerate extremal surfaces. They all have roughly the same area. Now, in this situation, if you want to compute some, say, Renyi 2 entropy, this is very similar to what happens when you're around the page time in black hole evaporation and you have two competing saddles. So roughly the idea is that once you compute trace of rho squared, the purity, what you get is the contribution from one saddle to the partition function times the number of saddles that you have that give you the same contribution. So when you then compute an entropy, you get that the entropy is given by the entropy of one saddle minus log of the number of the generated extremal surfaces. So this is just an intuition. I'll make this much more precise in a second. But the intuition is that once you have many competing extremal surfaces, you end up reducing the entropy. Great. Let me try to make this much more precise. So what we want to compute is the, again, Renyi entropy for simplicity of one side of this black hole after we insert all these particles. So what we need to do is set up some boundary condition for this calculation and then use the path integral to compute the entropy. Now, I'll be focusing on this large delta limit, and then I'll explain in a second why. For generic delta, you can formulate a similar puzzle, but things are much more complicated and not well understood. So I invite you to ask questions about that later. So for trace rho to the n, for example, you want to take the density matrix of one side, this rho r, and glue n copies to each other. And in each one of these copies, you have insertions of many particles. And then you want to use the path integral to compute this trace rho to the n. And this ends up being, in this simple model, just a sum over all possible weak contractions. And the nice thing about this large delta limit is that all weak contractions that end up with lines that intersect into the bulk are suppressed, exponentially suppressed in delta. So this implies that you can just sum over all possible weak contractions with no interaction, with no intersection at all. And each one of these weak contractions contribute the same amount. So roughly, this is just a combinatorial problem. So there is some factor of some propagator that is explicitly known. There is some topological factor of e to the sbps, which is true for this calculation. And then this combinatorial factor is called the Catalan numbers, just counts how many weak contractions you have. So great, you can do this, you can compute the entropy. What you find is SBPS, so the maximal entropy in the BPS sector, minus 3/2 log K. So you see that this is very, very similar to what Pratik found before, where you replace roughly K by beta in Pratik's talk by the number of insertions in the preparation of a state. So again, you're running a very similar problem to before. If you take K, the number of insertions too large, so you may put too many particles inside this black hole, you end up with a negative entropy, which is a quite puzzling feature. And the same thing, as I said, can be done in non-supersymmetric JT gravity in a microcanonical band, and also for generic delta, even though the resolution in that case is much more complicated. Now, the intuition for why this happens is very similar. Of course, as we all know, the JT gravity coupled to matter, the dual interpretation in terms of some matrix integral is much more involved. And it's not as well established as pure JT gravity. But in this regime that we are interested in, it turns out that you can describe this correlation function in terms of some Gaussian unitary ensemble. And I'll go back to that later in the talk. But the important part is that what you're probing is the spectrum of this one operator that you're inserting. You're inserting the same operator many times. And when you insert one operator many times, you're really zooming near the largest and lowest eigenvalue of this operator. And since the path integral takes some average, you see that there is, again, a continuum spectrum, and you're zooming very, very close to this continuum spectrum. And the density matrix eventually has support over a very, very small interval near the edge. And the effective number of states that you obtain by integrating the density of states on this small interval is less than 1. Now, we know that the entropy is positive when you have is 0 when you have one state. If the effective number of states you're probing is less than 1, the entropy goes negative. So this is very similar to the intuition that we had in JT gravity in Pratik's talk. Now, to solve this puzzle, again, we need to probe the discreteness of the spectrum near the eigenvalue with largest and smallest magnitude. So this is what the equivalent of what for Pratik was the ground state in JT gravity. Here is really probing very close to this and that edge, since you have a symmetric spectrum. So to do these again, we will need higher genus corrections to the path integral. And once again, at the disk level, as Pratik mentioned, all entropies that you can compute, annealed, quenched, semi-quenched, they're all the same at the disk level. But if you go beyond the disk level, then you obtain different answers for the various entropies. So again, we have to be careful and compute the right quantity, which ideally is the quench entropy, but there are all the difficulties Pratik mentioned. So what we will focus again on is this semi-quench entropy, where I remind you the difference is just that you compute from the annealed is that you compute trace row to the n first and then average in the denominator here. So I want to give you some idea of what the technical calculation looks like. I don't want to go into much detail, but roughly the idea is that if you have, you want to evaluate all possible weak contractions, now that done with lines that don't intersect, but now you also want to include higher genus. So in this case of the BPS set or JT supergravity, there is a nice feature, which is all diagrams for which you have empty handles. And by that, I mean that after you cut along all lines, you don't get a disk topology, but you get something like, for example, this cylinder topology. All these diagrams vanish. And this has to do with the fact that in the BPS set or JT supergravity, the trumpet vanishes. And this has been shown explicitly in these papers. Now, you might complain that I said that this is valid also for JT gravity, which is non-supersymmetric in a microcanonical band. And those diagrams in that case do not vanish, and that is true. But I'll go back to that because it turns out that those diagrams are actually, in the regime of our interest, suppressed. So you can actually drop them. But I will go back to that. So this fact, just let me give you two examples for simplicity. Say that we have a 4-point function. We consider this weak contraction, 1, 2, 3, 4. Then there is only one diagram here that will be non-vanishing, and is the one on a disk topology. If I add a handle, that would vanish. Similarly, for this weak contraction, 2, 4, and 1, 3, I cannot have this diagram because that has an intersection, and that's suppressed in this large delta limit. And I can have a genus 1 diagram that just works out. If I have a genus 2 diagram, I will necessarily have an empty handle, and so that vanishes again. So this is pointing to the fact that for each given weak contraction, you have one and only one diagram that contributes, and the genus of this diagram is fixed by the specific weak contraction. So the sum over weak contractions can be converted into a sum over genus. Great. Now, without the details of all this awful formula, the only point that I want to point out is that if you now generalize this, take n insertions per boundary and m boundaries, and you want to compute some correlator in this multi-boundary setup, all you need to do is sum over genus. You will have a topological factor that depends on the genus. And then you have some coefficients that all those coefficients are doing is counting the number of weak contractions that give you diagrams of that given genus. So these coefficients are known for one boundary. They're called genus-dependent Fari-Bruno coefficients, and we found them for m equals 2. And again, we want to look at this scaling limit in which we have many, many, many insertions. So k scales with e to the 2s over 3. And we are taking both k and e to the s to infinity. So it's this double scaling limit. But in this limit, it turns out that all terms in these coefficients roughly are offsetting this genus suppression. So all terms in this sum at each genus contribute at the same order. So what we need to do now is really take the genus expansion and resum it if we want to probe to correctly compute this correlation function. Now, this story becomes very similar in non-supersymmetric JT gravity, because in this double scaling limit that we're looking at, which is the regime of our interest where the entropy goes negative, empty handle diagrams that we saw before do not vanish, but they are suppressed by factors of e to the minus s naught times some genus. And so at each given genus, you will have diagrams that are suppressed by e to the minus s naught due to these empty handles, but those are at next order in e to the minus s naught, and in this double scaling limit they just drop out. So the important part here is that even in pure JT, non-supersymmetric JT gravity in a microcanonical band, the only diagrams that contribute a leading order in this sum are the ones that have no empty handles. So the combinatorial problem is the same. So now we have this, and this turns out that these coefficients simplify in this limit, so we could perform the sum. But instead of doing that, let me point out a slightly different approach to doing this resummation, which we found quite surprisingly initially, and then we explained from the matrix model side. So it turns out that each given, if you take this correlation function, and then you consider the contribution to the correlation function in this k over the e to the 2s over 3 limit at each fixed genus. So for example, you sum over all weak contractions here with, that end up with diagrams of genus 0. You do the same with genus 1. For the cylinder is the same. Then the sum of all these diagrams end up being precisely equal to what you obtain when you take pure JT gravity. You take the Airy limit that Pratik mentioned before, and then you compute pure JT gravity non-matter. You compute the partition function at inverse temperature equal to the number of insertions. So this is just a fact, which is true at every genus and every number of boundaries. So there is this strange equivalence between JT gravity with matter in this BPS sector and just pure JT gravity, non-matter, non-supersymmetric. You're just computing some partition function at inverse temperature. So this seems quite strange, but we'll see that from the matrix model side is actually arising pretty naturally. You can show this explicitly, including these factors of 2. And so, yeah, from the gravity side, it seems pretty mysterious, this fact. But we can use it to just compute the semi-quenched entropy by saying that this matter genus expansion we want to resum is just some JT pure JT genus expansion like the one Pratik was looking at before. So we can just take our calculation for the semi-quenched entropy, which in terms of genus diagrams, in matter diagrams, will look something like this. Just like for Pratik before, we had this resum disk with all possible weak contractions. And in the denominator, you will have a disconnected contribution and a connected contribution. This is very similar to before. Using the relationship from before, we can just translate this in terms of this pure JT genus expansion in the Airy limit. Once you do that, up to this factor of 4, this is the calculation Pratik did before. We can use these formulas and find that the semi-quenched entropy does not go negative. It actually goes to 0. If you were to do directly this resummation, you would find the exact same result. It's just 2 different ways to do the same calculation. So once again, what happened is that these higher genus contributions are super important. They contribute at the same order. But if you just resum genus and compute the annealed entropy, once again, the annealed entropy would go negative. And what really saves the day is this connected contribution in the denominator. So this is what guarantees that the semi-quenched entropy stays positive. And just like before, the positivity of the semi-quenched entropy proves that each member of the ensemble that I will talk about in a second for this operator has a discrete ground state. So it has some gap between the ground state and the higher energy eigenstates. And therefore implies the positivity of the quenched entropy as well, even though calculating that explicitly is complicated. Now, I want to spend a couple of slides on explaining this somewhat surprising equivalence that we saw here from the matrix model perspective. So the first important thing to realize is that in this large delta limit, any correlation function you want to compute for this heavy operator with large scaling dimension in the BPS sector, each diagram that you obtain can be mapped to a GeoHeap diagram. There is a one-to-one correspondence between a Gaussian unitary ensemble diagrams for a correlation function and the one that you obtain on the JT gravity coupled to matter case in this BPS sector. So this is just telling you that this operator with large scaling dimension is exactly modeled by a Gaussian random matrix. There is a one-to-one correspondence between correlation functions. And a large number of insertions, we are again probing really the edge of the spectrum of this GeoE. So we're probing the square root edge. Now, let me remind you what Pratik said before about the square root edge. You have this, for a very large class of matrix models, not only the GeoE, not only JT gravity, there is a square root edge, which means that the density of states just goes to 0 for these matrix models as a square root. And this is pretty general, but the other thing that is general is that once you zoom in near this edge and look at fluctuations of the eigenvalues, those fluctuations are captured by some generic universal behavior, which is given by this Airy distribution. So the square root edge is, let's say, in some sense, a saddle point approximation, and then you can look at how fluctuations look. And this blue curve, the Airy spectrum, gives you the probability of getting eigenvalues away from the square root edge. These are very small, but not 0. Now, the interesting fact is that this behavior is true for the GeoE, which is what is modeling our matter operator. But it's also true, as Pratik showed before, for JT gravity. So if you want to compute some correlation function with our matter operator, with a path integral, what you're doing there is taking the GeoE matrix model and computing this trace m to the 2k, where m is our operator. And you can do some algebra here and show that you have this correlation function in the limit of our interest, which is when k scales with e to the 2s over 3. Is exactly computed by an Airy matrix model partition function at inverse temperature equal to the number of insertions. So the point here is that we're really probing a regime which is very near to the edge and a regime which is universal in many matrix models. And this quantity is, in fact, the same thing that you obtain when you compute the partition function in JT gravity at inverse temperature equals to K in the SSS matrix model, as long as you're taking the inverse temperature, again, in the Airy limit, scaling with e to the 2s naught over 3, like predicted before. So you see that the fact that we're probing not the specific details of the matrix model of the operators, but just this regime in which you have a universal behavior for many different matrix models, implies that the answer you get is actually the same as the one that you get for JT gravity at inverse temperature equal to the number of insertions, just because the two matrix models have the same universal behavior near the ground state. And this factor of 2 is there just because you have two edges in the GOE and you only have one edge in the JT matrix model. So this is why this equivalence arises from the matrix model side is not mysterious. It's just a universal property of matrix models that are present in both cases. So if the only other thing I want to say here is that if you have K, so the number of insertions that scales with something much larger than e to the 2s over 3, then our bulk solution does not apply, in the sense that this resummation of the genus expansion breaks down. And to explore this regime, we can then rely on the matrix model. And in the matrix model, we just have this GOE. And you get eigenvalue instantons, just like Pratik mentioned before. So the idea here is that you insert this heavy operator, this correlation function of this heavy operator. And the correlation function, when you take the number of insertions of this heavy operator very large, ends up changing the dominant contribution to the path integral. It's, again, really enhancing members of the ensemble where we have one eigenvalue, which is far outside the continuum of the spectrum. So this is telling you that you have this different saddle point for the path integral with one eigenvalue separated from the continuum of the spectrum. And there is some subleading saddle, which is also very interesting, where you have two eigenvalues separate. And both of these saddles are very important if you want to match the results that you get in the resummation of the genus expansion in the regime of validity where both analyses are valid. Okay, I just want to give a quick summary and then some future directions. So we saw that we're computing some correlation function, JT gravity coupled to matter in the BPS setter, where you insert many, many particles. And we found that this annealed entropy becomes negative for one side of the black hole if you take the number of insertions too large. But this semi-quenched entropy, so this quantity that is able to probe the discreteness of the ground state of each member of the ensemble, stays positive as long as you include all higher genus contributions to the gravitational path integral. So this positivity is rescued by the resummation of all these higher genus contributions, and it's crucial to have connected contributions, so wormhole contributions that really guarantee the positivity of this semi-quenched entropy. From the matrix model side, you have that the solution is that the resolution of this issue is thanks to the specific statistics of eigenvalues near the edge. And this is captured by the Airy model in some regime and by the eigenvalue instantons in some other regime where we don't really know what to do from the gravity side. And these results imply the discreteness of the ground state. And this implies, in turn, the positivity of the quenched entropy. Now, I want to comment on a few future directions. So the first one is that the story Pratik mentioned before is very interesting and requires to really take into account off-shell contributions to the gravitational path integral. Well, this story is a little bit different in the sense that you have on-shell, all the diagrams that we consider, all these diagrams with handles where matter particles go through the handle, they're all saddles in the JT gravity coupled to matter. So that gives you a little bit of hope that maybe you could do a similar calculation also in higher dimensions, because you only need to look for saddle points of the gravitational path integral. Now, of course, that's a much more complicated calculation in higher dimensions. But it is in principle possible that you could come up with a similar puzzle and a similar resolution. And so the second point is this trying to compute this quench entropy from the bulk. Pratik mentioned already many of the issues with that for the no-replica trick. There could be a different approach that we're thinking about, where you maybe try to prove some generic feature of the matrix model first, and then use that, called the Airy kernel, and then use that to compute the quench entropy. It would also be interesting, and this connects to Huang's question from before, to interpret these one eigenvalue instantons in terms of some bulk geometry. So the issue with that is that, as it was mentioned before, that connects to some discussion of ZZ branes in JT gravity. But it's a little bit different from that, because for those ZZ branes, you just have some eigenvalue sitting at a maximum. It's really an unstable, it's not a new saddle of the matrix integral. In this case, it's quite different because it's a new saddle of the matrix integral, and the location of this eigenvalue is actually dynamical, and it depends on the number of insertions or the inverse temperature. So in that sense, it's a bit different from ZZ branes, and that's where the hard part comes about. And finally, there is this interesting question about generic delta. So everything I did so far relied on the fact that I'm using this large delta approximation, where I can throw away all diagrams where there are intersections. If I go away from that approximation and try to talk about generic delta, the problem is that there are many diagrams in which each intersection is weighted by a sig symbol in JT gravity. And that depends on the energies all around in the four patches around my intersection. And the problem with that is that you end up having a very non-trivial mixing between the energy spectrum of JT gravity and the spectrum of this operator. So the advantage of this large delta limit is that roughly you can only talk about the spectrum of this specific operator. When you go to JT gravity, when you go to generic delta, there is really some mixing between the energy spectrum and the spectrum of the operators, and then you probably need some two-matrix model for JT gravity coupled to matter, if that can be done. And there is some work on that, of course, but it's still far from being well understood. So we have some simple toy model to do that, but it's not quite satisfactory. It captures some features that we believe are generic, but it's not quite a whole story. So that's, I think, a very interesting future direction. And this is all I have, so thank you very much.
Can you comment about the computation of the von Neumann entropy in a thermal state from the gravitational path integral?
You mean instead of Renyi entropies? Yeah, that should not be probably too complicated. I guess you're talking more about the setup that Pratik was talking about. It requires some replica limit, obviously, that you need to compute the Renyi entropy for arbitrary n and then take the n to 1 limit. The replica limit is not expected to be as problematic as the no replica limit to compute the quenched entropy. So I think that should possibly be doable. We haven't attempted explicitly to do that, but I think it should not be impossible to do. Yeah. One?
When you consider these insertions of k operators, would you view this as, could you think about exponentiating this in the action and saying, you have the supersymmetric system and you add this small perturbation now integrated over time, so that you get something similar to the calculation you are doing when you do a perturbative expansion. Explain why.
So you're thinking of taking your trace m to the 2k and exponentiating it and including in some action. Yeah.
You start with a calculation which is you add to the Lagrangian term, which is the operator with a very tiny coefficient integrated over time. That in the low energy limit should be some non-supersymmetric system, because the operator would break supersymmetry.
Mm-hmm.
And then if you were to expand that, you get some diagrams which are somewhat probably similar to the ones you have, the large scale limit, perhaps.
Yeah, that's a very interesting question. We didn't think much about that. I can say that perspective is very similar to what you do in the matrix model side to compute eigenvalue instantons, where you have this trace sum to decay inserted, and you exponentiate it, and then you find a new saddle point. So you really find a new equation motion for the matrix model, and you find these eigenvalue instanton saddles. So that would be very interesting to look at it from the gravity side. We did not think much about it, but it's or at all. But I think it's a very interesting perspective. Maybe that could help us also understand what to do beyond the Airy limit to the eigenvalue instanton regime. So I think that's very interesting.
So can you explain to me again why you needed this two matrix model at the end? Just came by quickly to me.
Yeah. So the problem is that in general, if you have JT gravity, you have some matrix model that describes the Hamiltonian, and then if you add matter, in principle, it's possible, even though it's not entirely clear, that you could have a two matrix model where one matrix is the Hamiltonian, one is the operator, and then there is some interaction. Now, the good thing about the large delta limit that I've been working in is that there is sort of a decoupling between the two pictures. If you fix into a microcanonical window or into this BPS sector, you can roughly just look at the matrix model describing the operator. And the Feynman rules you use to compute this correlation function tell you that that is just a GUE, just a Gaussian unitary ensemble. If you go away from the delta to infinity limit, the problem is that now you need to be careful. You need to include interactions. And in particular, there will be weighings of interactions given by, intersection given by SIG-J symbols that also include energies on the outside. And once you start having 3 or more interactions, you end up having, even if you fix the energy in all the patches outside, so in your boundary conditions roughly, there will be some energy in the middle, some loop in the middle on which you have to integrate over energies. And that will lead you to have some non-trivial interaction between the energy spectrum and the spectrum of the operators. And so you really need to take into account for these possible two matrix models in order to solve this issue.
So for finite n system, for example, like SYK, this projected operator, the spectrum is bounded by the simple operator, right?
Sorry, can I say again?
The projected operator you're considering, the spectral statistics, its spectrum is bounded by the range of the simple operator, original simple operator, unprojected operator.
Okay.
So for example, the spin, then the range is bounded from -1 to 1.
Okay.
So that seems should set some constraint on the single value instanton because the lowest energy cannot be too low. You may not see in your analysis because you don't care about the but I wonder that should enter in if you consider.
Yeah, that's an interesting point. You were talking about double scale SYK, right?
It's the projected operator is bounded by the spectrum of the original simple operator. So if you
yes.
Model where you do a double scale now.
Right. Yeah, that's a good. Yeah, I agree.
Do you have any bulk intuition for why the sum over topologies should allow you to probe the discreteness of the spectrum?
Could you allow me to what?
Probe the discreteness of the spectrum.
Some bulk intuition for why it probes the discreteness of the spectrum. I don't think I have that. I don't think I can say much about that other than I'm including some non-perturbatory quantum gravity effects that, from the bulk perspective, that might be more sensitive to the underlying discrete spectrum of one single theory. But I don't think I have more intuition than, like more concrete intuition than that. Yeah.
Also about this higher dimensions, like
About this one?
the higher dimensions, like a lot of your calculations heavily relied on the matrix model, right?
Only the eigenvalue instanton calculations are in the matrix model. Everything else, like this genus resummation, for example, is all done from the.
Higher dimensions. What do you want to sum?
Well, in this, yeah, I agree that that's what I meant by it's much more complicated. The only point I was trying to make here is that in this setup, all these geometries that you have are on-shell saddles. They're not like off-shell geometries. So if you have a way to build these kind of geometries in higher dimensions, just on-shell, then you don't need to worry about, you don't need to really take care of off-shell contributions to the gravitational path integral, which is the thing we really don't know how to do in higher dimensions. So it could be that there is some version of this story that you could describe in higher dimensions, maybe using these shell operator states or something like that that allow you to have, in some sense, some handles similar to the A-squared model. But yeah, I don't have anything particularly concrete to say. That's why it was a future direction. But
I was wondering if you had something concrete in mind, or
the only thing concrete I have in mind is that you only need to look for solution of Einstein's equations with some heavy operator insertion, and that is plausibly doable. I don't know if you can do it for any genus or something like that. That's obviously much more complicated. Yeah.
Maybe just to add to that, just take that Riemann surface and multiply it by S2. That's, I think, what he means.
do you see this louder?
Take that Riemann surface and multiply it by S2 and allow the radius of S2 to vary over the Riemann surface. That's the ansatz that I think
That's cool.
I was suggesting.
Okay, let's thank Stefano again.